Hello students, good morning all of you. So today you are going to learn about null points and the fundamental parameters related to magnetic materials. Okay. So when we talk about this magnetism, these null points are very important for us for competitive exams. So let us see what are these null points and how we are going to find the null points. Okay, so null points. This null points also known as zero field points. They are also said to be as zero field points. That means here, suppose there are two magnetic fields. Say, for example, this is one magnetic field directed towards right. There is one more magnetic field that is interfering or combining with this magnetic field at this point. Okay. So the magnetic field induction due to of this magnetic field is B, and the magnetic field due to the second one is B, but opposite in direction. See this, direction is opposite. So means what? This is if I take the positive x-axis, suppose we are taking this positive x as positive and negative x as negative. Suppose this is the origin, this negative x we take it as negative, right? So then what happens here? This will be negative field and this will be positive field. Their magnitudes are equal and the directions are opposite. So as a result, what happens now? The net field at the point P, suppose this is the point P, we can write B net equal to B1, let us say this, suppose B minus B, that is equal to 0. So 0 magnetic field will be there at that point. That is, if we are going to keep a magnetic needle at this point, suppose we keep one magnetic needle here. One magnetic needle here. Suppose if I am going to keep a magnetic needle at this point, then it will show 0 deflection. 0 deflection. That's why they are called zero field point or null point. Null means what? No deflection. That's why it is called null points. So here this null point we can use for two magnets, and also when one bar magnet is kept in the magnetic field of earth. So two cases they may ask theoretical bits also. Suppose for example we keep a bar magnet, suppose this is a bar magnet here, for example this is a short bar magnet. The north pole of the bar magnet is pointing towards geographic north, because generally we take like this, no? This is our geographic north and this is our geographic south, right? So when the north pole of the bar magnet is pointing towards the north of the earth, then we get to two null points. That is, on the axial line, we are going to get two null points on the axial line. Okay. So one null point here at equal distance from the center of the magnet, another null point at equal distance on this side. Two null points will be there on the axial line. Now second case here, when the south pole of the magnet, so this is our bar magnet, this is the south pole of the bar magnet, this is the north pole of the bar magnet. Now you see the figure, the south pole is pointing toward the geographic north, means north direction of the earth, what we call geographical north. Okay. So, in that case again we have two null points. We have two null points, but that will be along the axial line now. That null points will be along the axial line like this. So, along the axial line, and they are equidistant from the center of the magnet. So, suppose this is our center of the magnet, they will be equidistant. Suppose here it is x and this will be also x. So, one point will be here outside the magnet and one point will be here. That is our null point 1 and this is null point 2. Similarly, here from the center of the magnet it will be equidistant, that is this is null point 1 at a distance x and this is null point 2 at a distance x from the center of the magnet. So, they are equidistant. In both cases they are equidistant now, and you have to remember this null point corresponds to the magnetic field of the bar magnet and the horizontal magnetic field of earth. The horizontal component of the magnetic field of earth will be equal. So, at null point we can write at null point we can write the magnetic field of the bar magnet will be equal to the horizontal component of Earth's magnetic field. So, that point you have to keep in mind here. B equal to BH. The magnetic field of the bar magnet will be equal to the horizontal component of the Earth magnetic field. Okay. So, that is the three important points that you have to keep in mind related to bar magnet kept in Earth magnetic field. But however, for problems they may not ask related to this, the theory point they may ask here, but for problem they will give two poles. That is, suppose there are two poles here, that is two magnet, let us say. This is one bar magnet, right? There is one bar magnet. So, south pole, north pole, and here another bar magnet, north pole, south pole. And the distance between these two center to center is d. Center to center is d. So, now let us suppose this is having magnetic moment m1 and this is having magnetic moment m2, right. One magnet, magnetic moment is m1 and another magnet, magnetic moment is m2. So, now here when this is the magnetic moment and d is the distance between their center, then m1 less than m2, recall our electrostatics. Always our reference is the smaller pole having lesser pole strength, their lesser charge. Here lesser pole strength. So, m1 less than m2 means the pole strength of the first magnet less than the pole strength of the second magnet. Now, another case, unlike poles facing each other, this first case. So, unlike poles facing each other. So, this is one bar magnet, or sometimes they may ask just like isolated poles also. So, this is the north pole, this is the south pole, and this is the second magnet. This is the second magnet here, south pole, north pole. That is, unlike poles, they are facing each other. Again, the center to center distance is equal to small d, right. Here also, this is having pole strength m1 and this is having pole strength m2. So, m1 less than m2. Now, recall our electrostatics. When like charges are kept at a separation, we know the null that is zero field point will be between them. And when unlike charges are kept at a distance of separation d, the null point will be outside the poles. So here in this case our null point will be in between the poles and nearer to M1, and nearer to M1, this is our null point which is nearer to M1, and here the null point will be outside the magnets. So somewhere here along the axis of the magnets, suppose this is the axis of the magnets, both magnets. Now the null point will be on the axis of the magnets, and this is our null point which will be outside, and it is at a distance x from our given pole, that is this pole. So for that, exactly similar to our electrostatic, here we are going to use the distance of null points, distance of null points x equal to x is equal to, so x is equal to d by distance between the poles divided by square root of m2 by m1 minus or plus or minus 1, right. So plus or minus 1, so this is up to this only, the root is up to that only we have. So here the root is only up to this. So root m2 by m1 only, m2 by m1 plus or minus 1. Plus is for like poles, plus we have to use for like poles, plus for like poles, and minus for unlike poles. That's very important here. Like poles are kept, then we will use plus sign, and unlike poles are kept, we use the minus sign. So that points that we have to keep in mind. Therefore, related to null point, these points that we have to keep in mind. So if at all they ask a numerical, then you should be careful about the sign. Like pole are facing each other, then you have to use the plus sign. Unlike poles are facing each other, then you have to use negative sign. So that is the point that you have to keep in mind. One is theory question related to bar magnet kept in earth magnetic field, and second one, isolated magnetic poles are kept either similar pole or dissimilar poles. Isolated pole means one north pole and one south pole, right. So that is the point that you have to keep in mind related to this null points. Okay. So now next important one we are going to learn is magnetic materials. Magnetic materials. So magnetic material means the material that are attracted by a magnet. Any material you take, if they are attracted by the magnet, then we call it as a magnetic material. For example, if you take iron or cobalt or nickel or steel, they are some of the example for this magnetic material. So related to magnetic material, we have to remember very important point, one point, that is Curie, Madam Curie and Faraday, they studied all the materials available at that time. Whatever materials available at that time, they studied about them, and they came to know that every material is having some magnetic property. Every material is having some magnetic property, but the only difference is some material can be strongly magnetized and some material can be weakly magnetized. So, weak magnetic material has been named as diamagnetic and paramagnetic material. So, weak magnetic materials, weak magnetic materials, weak magnetic materials. Example, they have been named as, not example, they have been named as, means two types of materials are there. One that is, we can write paramagnetic material, paramagnetic material, that is one type. They are weakly magnetized. And second one, diamagnetic material, diamagnetic material, diamagnetic material. Two types, diamagnetic material. This we will take up, and you already studied in theory classes. Theory, what are diamagnetic material, what are paramagnetic material. And second one, strong magnetic material, strong magnetic material, strong magnetic materials. These strong magnetic materials has been named as here ferromagnetic material, ferromagnetic material. So, ferromagnetic materials, ferromagnetic materials, right. Okay. So, later on I will tell you what are the important points that are required for our theory points of what do you call examination, JEE main or our MSET. Okay. So, here Curie and Faraday, what they discovered is this magnetic property is because of the rotational motion of the electrons and the spin motion of electrons. Because when you take electron, every electron will revolve around the nucleus, at the same time they spin around their own axis. So, combinedly that rotational, due to rotation there will be magnetic moment, because it is like a magnet, one electron is like a magnet, and due to spin it will have a magnetic moment. So, that combined magnetic moment of the electron is going to coincide for ferromagnetic materials. So, that when we keep this ferromagnetic material, they are going to be, when you keep in external magnetic field, all the magnetic moments of the electron, both rotational and spin, they align in the direction of the field. That is why they readily become magnetic materials. Okay. But when we take paramagnetic material, they are going to weakly align, and diamagnetic material, they weakly align, but in the direction opposite to the applied field. That is the difference between the three, right. So, all electrons moments will align with the direction of the field. Only few electron magnetic moments will align here in the direction of the field, whereas for diamagnetic material, few magnetic moments they are going to align, but in the direction opposite to the applied field. Suppose that means what? Here suppose this is the direction of applied field, right. So, now here the magnetic moment of this material will be opposite to that. Opposite to that. That is a basic difference between ferromagnetic material, paramagnetic material and diamagnetic materials. Okay. Now, to describe the magnetic properties of this material, we have certain parameters, means whether it is going to be a strong magnet or going to be a weak magnet depends upon some characters or some parameters. Okay. So, what are that magnetic parameters? Let we will see now, because numerical problems are often asked in this magnetic parameters. Okay. So, now let us see what are that magnetic parameters. Okay. So, magnetic parameters. Magnetic parameters or perimeters, sometimes we call them as perimeters also. Parameters are perimeters. So, first property, intensity of magnetizing field, intensity of magnetizing field, intensity of magnetizing field. It is a vector quantity and denoted by capital H, vector. Intensity of magnetizing field. Now, for example, there is a magnetic field in vacuum. So, this is our magnetic field. Say I am taking for example uniform magnetic field, and magnetic induction is B naught. Magnetic induction is B naught here. So, magnetic induction is B naught, right. Now, permeability of the free space, permeability of free space equal to mu naught, right. Now, the ratio of the magnetic field induction to the permeability of free space, we call it as intensity of magnetizing field. Therefore, here H vector is equal to B naught divided by mu naught, B naught divided by mu naught, B naught divided by mu naught. Okay. So, this is the intensity of magnetization, right. Intensity of the magnetizing field, that is, see the significance of this. See, when you take the actual magnetic field in which we kept the magnet, all magnetic line may not be allowed to pass through the magnet. Suppose this is my magnet. See, for example, this is our magnet. This is our magnet, right. When this is the magnet, this magnet may not allow all the magnetic lines to pass through it. Only a part of the magnetic line, suppose 20 magnetic lines are there, only 18 may be allowed, or 10 may be allowed, or 5 may be allowed. To know that how the material allow the magnetic field line to pass through, we are going to use this intensity of magnetizing field. So, that is the meaning of this intensity of magnetizing field. This is actual field and this is the field allowed to pass through the magnetic material. Okay. And its SI unit is ampere meter. SI unit is equal to ampere per meter. Ampere per meter. So, that is the SI unit of intensity of magnetizing field, right. Next, second property, we have intensity of magnetization, intensity of magnetization, intensity of magnetization, intensity of magnetization, intensity of magnetization. This is denoted by I vector, denoted by I vector. So, what is this I vector? That is, once the magnetic material is kept in external magnetic field, what happens? It will become magnet, whether it may be strong magnet or it may be weak magnet. Now, if we take the net magnetic moment of the material to the volume of material, that is the magnetic moment per unit volume, that we call it as intensity of magnetization. So, I vector we can write. So, I vector we can write here I vector. So, I vector is equal to, it is also a vector that is equal to m vector by volume of the material. This is the basic definition, and for this also the SI unit is ampere per meter. So, this is our basic definition or basic formula for intensity of magnetization. That means what? The direction of intensity of magnetization is that of the direction of the magnetic moment of the material, of the magnet. Okay. But this we can write another form also, that is for intensity, for that we know m. M is what? Pole strength into a magnetic length of the magnet. Therefore, that we can write I vector is equal to m into L, magnetic length of material is L, divided by volume area into length, that is the volume, and the direction is denoted by unit vector n cap. Then what we will get here? What we are going to get? LL gets cancelled. Therefore, here we can write it is not a, m is not a vector. So, it is, now we can write. So, in this case we can write like this. So, that is m by L into n cap. So, that is our another formula for this magnetic intensity of magnetization. And the SI unit of intensity of magnetization also same as ampere per meter. So, SI unit is ampere per meter. Already you know the dimensional formula. It will become L minus 1 into A power 1. Here also L minus 1 A power 1, L minus 1 A power 1, ampere per meter. So, this is another very important character, parameter to describe the magnetic properties of the materials. Now, let us go to another next property, that is third property. Susceptibility. Xi, Z like we write like this, one straight line like this, xi m. Xi, this is called as ZXi, xi, that we pronounce it as J. So, this J is the ratio between intensity of magnetization to the intensity of the magnetic field. That ratio we have been named as the susceptibility of the magnetic material. Therefore, susceptibility of the material is equal to I by H. I by H. But we know I units and H units are same, means Xi is a dimensionless quantity. It is a dimensionless quantity. We write susceptibility of magnetic material I by H. I by H, that is magnitude of intensity of magnetization to the intensity of magnetizing field. That ratio we have been named as the susceptibility. That is the significance of susceptible means what? He is more susceptible to diseases, means he is going to be easily attacked by the diseases. That means here, if the susceptibility of material is more, higher, material can be easily magnetized. And if the susceptibility is less, it will be difficult to magnetize the material. That is significance of this Xi. Okay. So, higher the value, higher the value, higher the value, higher the value, easy to magnetize material. Material is easily magnetized. Higher the value, material is easily magnetized. That's the correct word. So, material is easily magnetized. Material is easily magnetized. Easily magnetized. Material is easily magnetized. Easily magnetized. Because theory bits very important. Easily magnetized. And from this we can understand lower the value, difficult to magnetize the material. Difficult to magnetize the material. To magnetize the material. Okay? Magnetize the material. Right? The 2 points you have to keep in mind, and it is a dimensionless quantity because we know unit of I and unit of H is same. Right? So, that is the value that we have to keep in mind. Next property, that is fourth parameter, permeability. Permeability here, permeability denoted by mu, right. So, permeability means if we are going to take the ratio between the magnetic induction to the intensity of magnetization, that we have named as permeability. So, mu is equal to, we can write B by H. Mu equal to B by H, and its SI unit is, we can write here Henry per meter. Henry per meter, that is the dimensional formula will be M1 L1 T minus 2 A minus 2. That is the dimensional formula for this quantity, that is permeability. But here you have to remember permeability of medium and permeability of the vacuum, that is free space, two we have. Therefore, when we take permeability of free space, then we will write mu naught is equal to, here we can write like this, B naught divided by H. B naught divided by H, that is the magnetic induction in vacuum to the intensity of magnetization, that is one, and mu equal to B by H, right. But however, generally what we will do is, for any material, we are going to compare its permeability with that of the vacuum. That is, mu of the medium is compared with mu naught. Therefore, the mu value, we write mu r relative permeability equal to mu of medium divided by mu in vacuum. That we call it as the relative permeability. Means what? Already we have calculated the permeability. Permeability means what? You know, how many magnetic field lines are permitted to pass through the material. That is permeability. Therefore, here we can write mu is equal to mu r into mu naught. That is general formula that we are going to use, because I told you already mu naught, we know the value, experimental value, that is 4 pi into 10 power minus 7, so that we know the value, Henry per meter. Therefore, every time as you know mu naught, they will give mu r, so that we can calculate what is the magnetic field or what is the force, whatever it may be. So, they will give that value, right. Now, last one which often we come across, that is relation between mu r and xi, mu r and xi m. This is very important for us, because most of the time they are asking questions related to this formula. So, that relation we have here, mu r is equal to 1 plus xi m. This is the relation that we have between the relative permeability of the medium and the susceptibility of the medium, of the material. So, this is the relative permeability of the medium, and this is the susceptibility of the magnetic material. So, that is the relation between mu r and xi m. So, that suppose if we want xi m, then it will become mu r minus 1. So, xi m, suppose we want to calculate xi m is equal to mu r minus 1. So, this is also just another formula that we can use. So, these are the different parameters or perimeters that we are going to use to describe the characters of a magnetic material. So, tomorrow we will solve problems based on these parameters. Okay? Thank you.